Okay. I think I joined from different ID. That's why I'm not able to record. I did not join from MyQT ID. Got it. Now I understood why I'm not able to record. Okay, so let us start the session. If I know many people may join later, during that time, we will go back to basics as a question and answer session kind of thing. So big thanks to all for joining the session by MyQuantum Technology Private Limited Bengaluru on the occasion of World Quantum Day, which is 14th April. And the main purpose of this Quantum Day is for promoting public understanding of quantum science and technology around the world. Incidentally, the same day become celebration for few states in India as a happy Baishaki and Puttandu, Vishu, Pohle Baishaks, Boha Bihu, Bana Sankranti. And I think in Manipur also today is the New Year. I forget that day, how they are calling it. So for all friends from other states who are celebrating the New Year, Happy New Year to all. Good. With this wishes, let me introduce myself and our organization, which is MyQuantum Technology Private Limited. We fondly call it MyQT. And we are a learn, research, build organization, meaning that we are promoting learning quantum technology, researching on quantum technology, building quantum solutions. So we are into three verticals. This year, we are focusing on conducting training such that we are building the knowledgeable workforce on quantum technology. Predominantly, we are focusing on quantum computing and quantum machine learning. You will understand why we are focusing on these two things during my introduction. So our learning process includes self-learn. Most of us prefer self-learn considering our timeline, our availability, workload, pressure, all those things. Consider that most of us prefer self-learn. And some people who are interested to enroll for guided courses, that also we are conducting. And after we build a team of professionals, our research and build activities will start from January 2024. And this is our website URL. Please visit and you can learn more about our organization. Welcome again to our session. Thanks for joining. I'm waiting for a few more members to join because I have to talk about my. I will invite our academic counselor Deepa Vinod to start the session. Vinod, Deepa, are you able to?
Yes, KG.
Yeah, go ahead.
Shall I start?
Yeah, yes, Deepa, please go ahead.
Okay, good evening, all. And I'm very happy to be here on this very special day. Today is April 14th, and we know it's the World Quantum Day. And during this day, it's a very glad occasion to promote the public understanding of quantum computing science and technology around the world. So, here I am taking this opportunity to welcome all of you to this great occasion. And my name is Deepa Vinod, and I am academic counselor of MyQuantum, and I have about 5 years of experience in training sections. Then I would like to welcome our speaker, Mr. Karthik Ganesh Durai. We all call him very respectfully and lovingly KG. And Mr. Pradeep sir is also from IPT. Next, here I would like to tell a few words about MyQT. It's my quantum computing, as already told by KG, and what we are providing through this MyQT is it's an innovative quantum computing training and solutions. We provide many trainings and solutions to the upcoming term, that is quantum technology. Now, MyQT is a repository of the world-class knowledge and wisdom contributed by best minds in the field of quantum computing. MyQuantum technology operates across the globe through its vast network of affiliates and partner organizations. MyQuantum technology offers training, certification courses, research opportunity, and consultant services. And you all might have had a short introduction by KG. I would like to tell few words about him. That is Karthi Ganesh Dure. That is our KG. He is a software engineer who has turned into a data scientist who is working on building quantum machine learning solutions. And KG has master in computer application from NIEL LIT and Master of Business Administration from Puducherry University. Currently, KG is working as a chief quantum architect in Boson Q PSI PVT Limited, and he's a co-founder of Quantum Computing India from November 2019. KG worked in Dell Technologies Bangalore, Synergy Consultant Singapore, Kebil Shipyard Singapore, and OILAM International Singapore. Hailing from Karaikal, Puducherry, KG is relocated to Bengaluru on 2013. A tech survey intrigued by physics, mathematics, and technology. As a part of his 8 years of data science career, KG built mission critical AI and ML solutions involving big data and Python technologies. Now, here again, I take this grand opportunity to welcome each and everyone to our short session, that is for 2 hours, and you will gain a lot of knowledge. As a starting, we'll get a short, not a very short, a very elaborated knowledge on the introduction to quantum computing. And once again, I welcome each and everyone, those who have joined us during this wonderful evening. Welcome one and all.
Thanks, Deepa. Thank you. Thanks for the introduction. Team, let us start the introduction to quantum computing. So, in 2023, the word quantum is the most talked buzzword. Yesterday, I had a chance to attend IBM session on 25th anniversary on IBM research, where it is on general topics, but quantum computing was frequently referred by eminent speakers, be it government or be it academicians, everyone more interested, and then they are betting on quantum computing as the next technological growth. So, and this is a great opportunity and then occasion to talk about quantum computing. And this session is a kind of knowledge sharing session. I request whoever have idea, please come forward, share what you know, ask questions such that other team members who are joined, they are also will learn a lot of things. And please keep sending on message on the chat window, or else there is a WhatsApp group exclusively created for MyQT community. You can join there and then you can ask questions there also. Those questions will be forwarded to me. I will answer those questions. Make use of this session and help us to learn as a team, because I know how difficult it is to learn quantum computing. I will tell when I tell the history of how I started learning, and you will understand how it is useful. Before starting anything, just I want to show few working computer list of quantum computers. This first one, what you are seeing here is this one. This is IBM quantum computer, and this is the world first working quantum computer. And IBM started building quantum computers since 2007 itself, but the commercial product came in the year 2015 only. And this one is Google Sycamore, and this one is Ion QX. Then this is D-Wave system, and this is Xanadu Borealis, and this is Rigetti. Here, IBM, Google, Rigetti. These three systems are built on technology called superconducting quantum computers. And D-Wave system is built on a technology called quantum annealer. And Ion Q harmony is built on a technology called trapped ion. Xanadu Borealis is built on linear optical circuit. Now you may hear, we know classical system, it is always semiconductor only, right? But here there are multiple technologies. That is one of the biggest challenge quantum computing industry is facing now, because there are multiple ways to build quantum computers. But predominantly superconducting quantum computers are common in place. That's why we have IBM and Google and Rigetti. These three organizations have built superconducting quantum computers. Why I'm showing this one as a first slide? Whenever I'm talking to many people, people are skeptical about quantum computers. Is it possible to build quantum computers? Because quantum computers are noisy, they are fragile, they have a lot of inferences impacting the entropy. These terms are I used to hear. And people used to tell that it is very difficult to build quantum computers because they need temperature cooler than the outer space. How to build all those things? So there are a lot of skeptical views on working quantum computers. That's why I am starting the session with list of working quantum computers. So this list gives you a confidence. Yeah, there are working quantum computers. So we are seriously can pursue career on quantum computers. To give that confidence only, I have started with this slide. Hope this slide serve the purpose. If anyone has still having skeptical about the quantum computing, please shoot out your question in WhatsApp. I would like to hear and then answer. Of course, not during the session. Post session, I will answer, or else either Pradeep or Deepa or any other team member who knows the answer, feel free to answer the question. Now, moving on to the next slide. I think I have to remove this pin. Okay, now actually, what is quantum computer? We used to talk about quantum computer. What is quantum computer? Quantum computer is built on principles of quantum mechanics. Then obviously you want to know, oh, what is quantum computer? What is quantum mechanics? So this is one thing what you should be aware of quantum computer. There will be unmanageable information overload. It will be overwhelming. When we start reading one sentence, some word will come. Oh my God, I don't understand. Then you have to go and then Google for it. When you come back, the new word come. Then that kind of information overload you will experience whenever you are started learning quantum computing. So stay with me, don't worry. As a trainer of a lot of experience, I know where to stop. So quantum mechanics is a branch of physics. It should be called quantum physics, but traditionally people started calling quantum mechanics. We are also started calling quantum mechanics. Actually, it is not mechanics, it is a physics, quantum physics. Any physics other than quantum physics is called classical physics. Obviously, all our Newtonian physics, they are all classical physics. Quantum physics deals with the subatomic scale. Quantum computer operations are based on linear algebra of complex numbers operating in Hilbert space. Here, I would like to call out our digital computers, laptop, desktop. They are based on Boolean algebra of Boolean number, binary digits. But whereas quantum computers are operating on based on linear algebra operating complex numbers. Now you will realize why quantum computers are becoming powerful. And building blocks of a quantum computer is qubit. We are going to learn more about qubit in next slide. Since they are operating at subatomic scale, they need sophisticated engineering capabilities for um, avoiding noise, inference, and impact of external system. And then they have to operate in very cool temperature. Because of all these complexities, as of now, a quantum computer will cost 15 billion to 25 billion approximately. There are few systems, 5 billion, 7 billion budget also they are building. But to build scalable, powerful quantum computers, we need 15 billion to, uh, my apologies, 15 million to, sorry about it, is 15 million to, what happened? Okay, sorry. It is 15 million to 25 million, not billion. Yes, I will share this deck with you. So that's why I want to correct immediately. I don't want to. Okay, sorry about that one. So 15 million to 25 million approximately, it will cost approximately. Now you may interested to know how, what are the components there? Whatever you're seeing now, they're real gold. Now you will realize why it's become very costly. So as I told you, remember, um, quantum computer is built on principles of quantum mechanics. So now you may want to know what are those quantum mechanics. So we call it as a quantum behaviors, which is called superposition, entanglement, and interference. I will come back to this slide and explain in detail. For the time being, just remember there are three words: superposition, entanglement, and interference. These are the quantum behaviors based on which we are building quantum computers. So whenever we are talking about the quantum computers, we are dealing with the three behaviors: superposition, entanglement, interference. So this is enough as of now. I will come back and then explain what is superposition, because there are a lot of things easy to understand in coming slides. After discussing, if we come back, that will be useful. That's the reason why I'm skipping the explanation for these things now. So now you heard it is built on qubit, right? Obviously, you want to hear what is qubit. So qubit or quantum bit is built using subatomic scale particles like electron or photon. Now you will realize it is built on electron or photon. I'm not sure how many of you here from semiconductor background. If you are from semiconductor background, you remember very well that in semiconductor, there are thousands of electrons forming a transistor. If the electrons are ground level, it is 0 bit. If they are moving to energy level, excited energy band, it forms a circuit and it is called 1. So thousands of electrons are used to build transistor in the classical computer. But whereas in quantum computer, a qubit is built using only one electron. That's why we call it as SET. We call it as SET, single electron transistor. Or else we can use photon also. And there are many communication network using photon. But most of the processing elements are still single electron transistor only. So these electrons are represented using a circle or sphere, which is called Bloch sphere, which can be in 0. We call it as a 0 ket. You can see here, it is not just a 0. It is a vertical line, number 0, and a bracket. This is called 0 ket. Similarly, instead of 1, they are calling it as a 1 ket. Now you will wonder why not 0 and 1? Technically, they are vectors. So this is a notation proposed by Baldirac for representing vectors. That's the reason why they are called as a kit. It is popularly known as kit notation. So we are using kit notation for expressing the value stored inside qubit. As of now, this is enough. Um, as a recall, I'm telling you, we are using single electron to represent information in quantum computer, which is called qubit. The information can be 0 ket or 1 ket, or sometimes, see, you see here, it is, this place is 0 ket, this place is 1 ket, right? Somewhere, sometimes, if an appropriate energy is applied, the energy of the electron, the spin, which is called the spin of electron, can move somewhere inside the electron, which is called psi-ket. This is called superposition. Now you will wonder, what is the superposition? Uh, now I want to go back to this slide. You see, a quantum system can exist in multiple states at the same time. So how this industry is trying to understand this one? The electron here, I'm referring, the spin is the energy of electron, which either may be in the north pole or in the south pole, or if some energy comes, it were somewhere in between north pole and south pole. So that time, assume that the energy is rotating here. I can say certain percentage of 0 ket, certain percentage of 1 ket. Now the psi-ket is superposition of 0 ket and 1 ket. That is what they are referring here as a quantum system can exist in multiple states at the same time. So when you read it separately, it looked like something, how it is possible, all those things. But when you visualize with this blow sphere, it may help you to recall. But still you may think, KG, it is still unclear for us. It is something you are talking. Please talk in English. You may ask me, because I heard many times whenever I explaining this blow sphere with the 0 ket, 1 ket, they used to stop me. Hey, please talk in English. That happens with the quantum computing frequently. So if you feel that, hey, what is the superposition? I would like to explain with an example. I have a coin here. So, right, the coin, we know very well, the coin has only two position, either head or tail, right? We can consider this as a binary system. We know that it is a 0 ket or 1 ket. Now, I'm going to toss this coin. Okay. Some of you choose head. Whoever choose head, raise your hand in the MS Teams. Can I expect at least 50% of the attendees to raise their hand for head? I'm going to toss it. So select, whoever select head, please raise your hand in the Teams. Yeah, I would like to wait for a few more seconds. Not microseconds, it is pure seconds. So we have some time. Yeah. 10, 1010, 1009, 1008, 1007, 1006, 1005, 1004, 1003, 1002, 1001. Okay. Now I'm going to toss it and I hold like this. If I hold like this, is it head or tail? Now you can't tell whether it is head or tail. You can tell that certain percentage of head, certain percentage of tail. So now this coin is in a superposition. Hope you are now things may get clear to you. Okay, this is how the superposition comes into system. And you won't believe the nature is always quantum. The nature is always in superposition. But we are thinking that it's binary, but it is always superposition. Now the energy, the energy means, assume that this is an electron. This electron has some energy inside this. Let me put this is, yeah, I put energy. So this single electron, it has some energy inside that one, right? If I rotate like this, or instead of this one, if I apply a magnetic source, very powerful magnetic, like MRI scan, nuclear magnetic, that's kind of magnetic that can control the energy inside this electron. So that energy, if it is goes to top, which is north pole, that is 0 keV. For it is come to south pole, it is 1 keV. For any reason, if it is in between, that is psi keV, which is in the superposition. Hope this demonstration helps you understand what is superposition. Okay. If any of you have any question, please ask. I'm ready to answer this question because we just uh, demonstrated one of the important concept in quantum computing, which is superposition. Any question from anyone? Okay, I'm assuming that no more questions. Since there are no questions, let me move on to the next slide. This one will help you. Yeah, go ahead. Yeah, yes. Hello. Hello. Someone is asking question. For any reason, if you're not, please type in the chat window. Okay, I will. Is there anything in the chat window? Deepa, if anyone asked a question in WhatsApp, please stop me and then read out the question or paste in the chat window.
Sure, KG.
Great, thank you. So let me continue. So this image will help you understand more clearly. This is a life or what is called a real life example. Imagine that there is a football ground, 10,000s of footballs moved to one goal post 0 and moved to other goal post 1. That is what really happening in the semiconductor. But whereas in quantum computing, we have only one single football, which is one single electron. This single electron has some energy inside that electron. We are using that energy to represent qubit. It may be either 0 keV or 1 keV or in between psi keV, which is a superposition. So this example will give more clarity on the quantum bit, qubit. Now you will realize because of the single electron system, quantum processing units are in the nanoscale and they are operating at subatomic scale, meaning that we have to go to subatomic scale. It is not an atom. Go inside an atom. Inside an atom, you will see nucleus. Inside the nucleus, you will have nucleus and then proton, and there will be energy band. In the energy band, the electrons are rotating, right? You are going to that level. That's why it's called subatomic scale. So under subatomic scale, matters obey quantum mechanics. Classical physics will not work there. If any of you have seen the movie Ant-Man or Avenger, you will be able to visualize that quantum realm. They are called as entering into quantum realm. So the quantum realm is in this subatomic scale. It may help you, but those are fiction. But we are talking about the science. When we are talking about science, obviously we have to mention about mathematics, right? Before jumping into the mathematics part, now you may have a question. KG, is it possible to build that kind of system which can be in a cycle, meaning that both superposition, how it is possible to build? Just now I demonstrated the coin, right? Like that, we can build using superconducting material. Superconducting material, or as the name suggests, they will conduct the current without any resistance, meaning that the instant the energy or current passes through, it will reach in the destination. source to destination reach without any loss. That is superconducting. The challenge is that they won't operate in normal temperature. They will operate in a super cool temperature. To be precise, it is minus 273 degrees centigrade. It is cooler than the outer space. Then another technology is called trapped ion. Ion is chargeless particles. Those chargeless particles, if we trap them within a within a setup or within a system, they used to stay in the both superposition. And there is optical lattices. Optical lattices are like um, with a with the application of a laser beam, certain photons, whether they will be in the in the top or in the bottom, in the valley or in the summit. But with application of laser beam, we can make them stay in between the mountain range or slope. If it is in slope, that is a super position. Like that, there is a quantum or coupled quantum wire, NMR, nuclear magnetic resonance, then solid state NMR, electrons on helium, these electrons on helium, then CQED, magnet. There are many other things. My favorite one is the optical lattices built. And there is one more thing called diamond nitrogen vacancy. These are all various techniques to build quantum bits. So after building the quantum bits, we can arrange them next to each other, then build the quantum circuit. It looks like easy, right? Let us see how easy it is. I would like to take up question. Anyone have any question? Because I don't want to just go through the topics. I would like to just give a break. If you have any question, I'm ready to answer. Any questions? Deepa, is there any question in WhatsApp?
No, KG.
Very good. Okay, then let me continue to the next step, which is, so far I'm talking a lot of things, right? And you may feel, oh my God, unless we at this Friday 6 p.m. we joined a session and then this guy comes and then talks something, whether it is English or non-English, we don't understand. If you think like that, you are not alone, because the quantum mechanics, it is not easy to understand in first attempt. You need multiple repeated, how to say,
Excuse me,
repeated
KG.
recall. Yeah,
There's a question in the chat box.
yeah.
Sir,
Okay.
what?
Sir, what is the reason that it operates in the very cool temperature? That is a very good question, Shanmay Priya. See, when I talking about the superconducting, I told there is no loss in the energy transmission or the current flows, right? If there is a normal temperature, the energy will dissipate because of the temperature will break the bond in the electrons or molecules. The molecules will escape. That is the reason why you can see little bit resistance in the normal temperature, in normal conductance or normal conducting materials like aluminum, copper, iron. Those materials are normal conductors. These, there is a loss. That is the reason why there is a resistance. But superconducting materials are they won't allow any loss. How they will bonded together without loss? Only if they go to lowest temperature, they will be able to operate without any loss. If the temperature increases, the molecule loss or energy loss will be more. They can't be a superconducting material. That's the reason why they have to go to that kind of low temperature. Hope that helps. Cool. So now let us continue. And this quote is by Richard Feynman. And when it comes to Richard Feynman, I would like to recall an incident. In 1956 or 57, Richard Feynman is the first person who proposed that we can use quantum mechanics for building computing devices. At the time, everyone, as usual, scientists, people cannot understand what scientists proposing, right? Everyone, um, the whole scientific community, engineering community did not consider his proposal. They thought that it is engineering nightmare. We can't build quantum systems. But again, in 1981, Richard Feynman proposed a detailed plan for building quantum computation along with Bernard Benoit. So that is the first doctrine or first proposal from scientific community to build a computing device using quantum mechanics, which they named as a quantum computers. So again, I'm telling, build a computing device using quantum mechanics, which is called quantum computers. And that idea was proposed by Richard Feynman. And it was built as a full-fledged system by many scientists, but the first proposal came from Richard Feynman. And there are many other scientists who introduced the the word quanta. There is a number 6.627 multi into 10 to the power minus 34 joules per second. That is the quanta of energy of photon packets. That was given by Max Planck, who is considered the father of quantum mechanics. And there is another equation given by wave equation, the psi-ket, which was given by Erwin Schrödinger and Dirac, who gave the atomic calculation and then Ket notation. Like that, there are many scientists who contributed to quantum mechanics, and that's we are going to see in next slide. Before that, just I'm not able to stop telling about Richard Feynman. I am a fan of Richard Feynman. So, so if you don't understand, you are not alone, which means you need to read these things again and again. So we will share this deck in the WhatsApp group. So those whoever have not joined, please join there. I will share this PDF version of this deck there. You can read multiple times. And whatever questions you have, you can ask in the group also. With that, I'm moving to the next one, which I want to, because I'm talking a lot of things about quantum, and you might have feel that KG, please, it is overwhelming. Stop. Tell me something which I know or which I can easily connect. With that in mind, I'm talking about digital computer. Digital computer, all of us know, a desktop or laptop. I'm an ex-Dell, so obviously I prefer and I like Dell laptops. That is one reason why I'm having these things. Because I have to call out because I was associated with the Dell. That's why these pictures. If you open any desktop or laptop, you will see motherboard, right? Inside CPU, you will see motherboard. Inside motherboard, you will see inside CPU, you will see motherboard, graphics card, RAM, HDD, battery, processor, microprocessor. If you try to see what is inside the microprocessor, you will see instruction register, program counter, decoder, multiplexer, arithmetic logic, accumulator. Like this, you will see. Whatever I am telling now, hereafter, only people from digital electronics or computer science, they only can understand. But for others, they can connect few dots. So like this, there will be something in quantum computer also, right? Like this processor, all those things like this, there should be some components in quantum computer also. That's what we are going to see in the next slide, architecture of quantum computer. So this architecture will look like chandelier, the hanging lights structure everywhere. Even if you see the first list what I have showed, all the systems are hanging like this chandelier model. There is a reason for that one. The actual processor is here at the bottom. This is where you hope you are seeing my marker. I'm marking with the red color. This is where the processor. So in this very big bulky infrastructure or bulky system, the quantum processor is at the end of the hanging structure. Remaining things are just to support. What are there? A qubit signal amplifier, then input microwave line, then superconducting coaxial lines, then cryogenic isolators for cooling, then mixing chamber, then quantum amplifier, then cryo-permanent field protector. This much of components are there to protect this quantum processor. Why? Because quantum processor is operating at subatomic scale. At subatomic scale, the inference is very fragile. Even a cosmic behavior will impact. So we have to protect the system. That's the reason why we have this much of uh, bulky structure. Here you can see the cooling power is minus 273 degrees Celsius. Maybe this picture may look like KG. I'm not able to read very clearly. Is there any clear picture? Let us see the next image. That will give you more clear architecture. It's a kind of block diagram. So here you can see the processor is here, quantum processor. This is the refrigeration unit, which is giving minus 273 degrees Celsius. And this is the classical data. This classical data is encoded into quantum information. So the encoding is very, very important because quantum processor, as I told in the beginning, quantum processor operating complex numbers, not binary numbers. But our classical data, binary data is in the binary format, zeros and ones. That zeros and ones need to be converted into 0-ket, 1-ket or psi-ket. That conversion, or we are in quantum computing, we don't call them as conversion, we are calling them as an encoding. A classical data is encoded into quantum information. That encoding is happening in these places. That encoded data is transmitted to the processor using superconducting lines. Those superconducting lines they will respond to the what is the outside world, or the system will affect. That is the reason why they are protected into the electromagnetic shielding, radiation shielding, these kind of shieldings. Okay, this is the architecture of quantum computers. Now, things may make a little bit clear to you, those who are attending. First thing, let me review the things, then I will go with the timeline. First, I started with the list of working quantum computer. Again, those are a lot of people joined today after this session. So I would like to express my greetings for the Quantum World Quantum Day, which is April 14th today. And few of our friends who are from different states, they are celebrating New Year. And for all of them, very happy New Year. Now, I'm recalling. It's a kind of whatever we have discussed, we are recalling. This is about MyQT. So this is working quantum computers from IBM, Google, Rigetti, IonQ, D-Wave, and Xanadu. Then I talked about what is a quantum computer, and it is based on quantum mechanics. And the important part is it is operating on based on linear algebra of complex number operating on Hilbert space. See, one thing I would like to stress, you have to always remember these three words. Whenever it comes to quantum computer, remember this word. Quantum computers are based on linear algebra of complex numbers operating on Hilbert space. The moment you recall these three words, you can understand how powerful it is. Because classical systems are operating on Boolean algebra of Boolean numbers. But here it is complex numbers, because complex numbers can represent any data without approximation. That I'm not sure whether I will be able to explain the word without approximation, but some of you can connect this word. Without approximation is the really powerful computation capability. With this, I moved on to explaining. I did not explain these things. I explained only superposition. Entanglement I will explain later. Where I explained how a single electron can be in the superposition by demonstrating tossing a coin and then hatching it vertically. Then I showed this example or analogy where a football ground, thousands of football used in the semiconductor world, thousands of electrons, then one single electron similar to one single ball. This is what quantum bit. Then we discussed how we can build a quantum bit or qubit using multiple technology like superconducting, trapped ion, optical lattices, quantum dot, coupled quantum wire, NMR. These are the various technologies to build quantum computer. But now you can remember, even though there are this much of technologies, the industry is able to build quantum computer using only these three technologies. Now you can recall IBM, Google, Rigetti. They are building superconducting quantum computer. IonQ, Honeywell, they are building trapped ion. Borealis, Xanadu Borealis, that was built on optical linear optical. It's not optical lattices, but it is optical quantum computer. And D-Wave is using, that is also superconducting, but on annealing. It is not a quantum computer. So this is what we discussed. Then I told, if we don't understand this, okay, because Richard Feynman himself told that it is very difficult to understand. Then I talked about Richard Feynman. Then we discussed about the architecture. Why architecture? That will give you a flavor or a confidence that these are the components inside the quantum computer. That's why I compared with the digital computer. The reason is that we are familiar with the digital computer, laptop or desktop. We can easily connect. That's the reason why I brought architecture of digital computer here, then moved on to architecture of quantum computer. Okay, this is what we discussed so far. Win this discussion, any question? If you have any question, please ask in WhatsApp. We will answer. I'm considering there are no questions. Deepa, are there any questions in WhatsApp?
No, KG.
Very good. Okay, let us move on to the next. It is a kind of history. I like history because that gives us, or it will help us to appreciate what we have achieved so far. So in 18th century, in 18th, we have the double slit experiment. These are all quantum mechanics. You note that this is quantum mechanics, not quantum computers. So then there is a black body radiation, Planck's constant, then Dirac notation, then wave particle theory, which explained the matter are in the both wave as well as particle. Then EPR paradox, Schrodinger cat. Then there is NMR, superconductivity, 1950s. Then 1960s, quantum entanglement and quantum operator. These are mathematical operations. Then in 2000, quantum machine. There are many things happen in the quantum mechanics. But we are studying quantum computing. So let us discuss about the timeline of quantum computing. And it is conjugate coding. It's a mathematical operation. Conjugate, if you recall complex number, a plus ib, the conjugate of a plus ib equal to a minus ib. That based on that, there are some few coding systems developed. That was the conjugate coding. I'm not going to explain everything because if I started explaining, I have to enter into mathematics, and I know everyone will. So I'm not talking about mathematics now. Then superposition, then quantum information theory. Remember, I told uh, um, Richard Feynman proposed to quantum information theory. Then universal quantum computer in 1980s. That is where Richard Feynman and then Benoit proposed a computing device. Then quantum annealing. Then 1990s, there is entangled based communication, Simon algorithm, Shor's algorithm. So here I would like to take a break, or I would like to stress this Shor's algorithm is one mathematical formula proposed by Peter Shor, who is a professor in MIT, USA, Massachusetts Institute of Technology. This Peter Shor algorithm, it is just nothing but finding the prime factor of very large integer number. But it is a factoring problem. But that one problem made the defense or military of all nations and financial institution wake up to the quantum computing call. Everyone got, oh my God, this is very, very dangerous. And everyone started seeing quantum computer as the villain, meaning that with the Shor's algorithm, a quantum computer can break any of the encryption or cryptography system what we are using now. Think about your ATM pin can be broken, or can be hacked within few minutes. In current technology, with the classical system, that will take many years to break a very large number into two prime numbers. But Shor's algorithm with a powerful quantum computer of 1000 qubits or 1200 qubits, it can break any cryptography within 4 to 8 hours. Years of computation can be reduced to in terms of hours and minutes. That is the danger proposed by, or that was the dangerous signal from Peter Shor to the world. Hey, you have to wake up for the quantum computing. Then there is another algorithm by Growers, which happened in the 1996. This is 1994. This is 1996. These two algorithms convinced the scientific world that, hey, this is right time to research on quantum computing, because mathematically it is proved that the operations are possible. It is only the engineering efforts to build a computing device based on the quantum mechanics. That is the message conveyed by Peter Shaw through his algorithm. Today, we are having this kind of funding efforts, worldwide efforts, all because of, I would say, Peter Shaw. Because Peter Shaw frightened the world. Hey, my algorithm can break any of the security or cryptography algorithm. That is the message. So that is one of the important event in the quantum computing history. So with this history, I'm moving on to the next slide. I know there are no questions in this one. Let me move on to the next slide. This is quantum computing ecosystem. So this is as of 2022, last year. I checked for this same quantum computing ecosystem in 2017. I saw only 12 organizations in this picture. But now you see how many companies are operating on quantum computing domain. There are a lot of organizations. See, hardware and components, we have IBM, QM, Quantum Mechanics, NKLIT, Mabel, IC. There are a lot of things. And then QPUs, quantum processing units, Rigetti, IBM, AWS, D-Wave. Then see here also ion trap, neutral atoms, silicon, photonics, others technology like that helium, electrons on helium, and nitrogen vacancy in diamonds. And software side, there are Microsoft, Q Control, Classic, Autos, all those organizations. And application side, there are many organizations, AWS, Azure. Here, the Azure is providing a solution called Azure Quantum. They have built their own quantum computing language called Q Sharp. So if you want to pursue quantum computing career, you can learn a language called Q Sharp and then start writing programs for quantum computing. That was offered by Microsoft. And other organizations are relying on Python. That we will cover later. And here also our company, Boson QSci, we are into building quantum computing enabled computer aided engineering simulation. All sounds very fancy. Indeed, it is one of the very highly complex scientific problem we are trying to solve using quantum computers. And also MyQuantum technology, we are focusing on training because we are strongly believe that building a workforce is precursor for entering into any research or building activity. That is the reason why this whole year we decided to stay in the training domain. And we are into the prior to the MyQT, we were part of Quantum Computing India. Still, it is there. We are conducting sessions through Quantum Computing India also. That is also a non-profitable organization. But whereas MyQT is the private limited commercial organization where we are providing committed services on commercial basis. So this is the ecosystem of quantum computing. And when you get this deck, you can go in detail, explore about each company's organizations, what they are doing. That will be really very interesting, and then it will be motivating to pursue quantum computing career. Any question there? I heard some message. Is there any question? Okay. If not, let me move on to the next slide. Any system, it is a computer. Obviously, there will be software, right? So if you want to build something for quantum computing, what are the softwares? IBM is offering a framework called Qiskit, which is based on Python. Then Google is offering a framework called SIRQ, SIRQ. Rigetti is offering PyQuil or Forest. D-Wave offering Ocean. Xanadu is offering Strawberry Fields and Penny. Microsoft offering both Python as well as QSharp. For your information, I have experience in Qiskit, SIRQ, hands-on experience, but I know other things also. Penny, then QSharp. Because you should know as a trainer or facilitator, these are my skill set. I'm hands-on into these 4 technologies where I'm building solutions. Predominantly, these are all proof of concept or a toy problem to convince the industry that it is possible to use quantum computer for your problems. But the production quality thing, still we are waiting for a 1000 qubit system. As of now, the highest number of qubit is offered by IBM called Osprey, the IBM Osprey processor having 433 qubits. That is the highest number of quantum systems available in the market now. With the 433 qubits, we will be able to build only proof of concept problem only. Production quality systems we are not able to build. That's the reason why we are moving to a solution called quantum inspired algorithms. That is what we are working. Boson Q side, we are working on quantum inspired algorithms for this year and next year. In the meantime, we are expecting 1000 qubit systems will be released by IBM in 2024. That's what they committed. We are also strongly believing that 1000 qubit system will be in the market in the year 2025. Then we will be able to build production systems. Then at the time when production system comes, the demand for quantum computing professionals will shoot up like anything. And now this is the comparison of those frameworks: IBM Quantum, Amazon Bracket, Azure Quantum, then Google Quantum Cloud Services. This is for who wants to pursue quantum computing. They want to choose whether I have to go with IBM Quantum or Azure Quantum or whatever it is. You can compare and then make a decision. That's the reason I bring it here. Now, after hearing all those things, okay, it looks like something very powerful computer you are building where I can use. So now we are focusing on applications of quantum computing, artificial intelligence and machine learning. Now, this is my area because I'm a data scientist who have hands-on experience in building AI and ML solutions for industries on multiple domains. My domain is supply chain management and logistics. And also we call it as a hardware optimization. That is also my domain. In those domains, I built solutions for business problem using AI and ML, using classical system. That is my hands-on experience, my previous job. So I'm able to leverage that knowledge to build quantum machine learning related solutions. So now you can see the logical progress in my career. So for software engineers, if you are from software development side, you can straight away jump into quantum computing because you need a domain to transfer or to pursue your career into quantum computing career. And other things are something different domain. The chemistry, computational chemistry. I have one of my friend who is a PhD in chemistry. He is specialist in um, some protective kind of chemistry. Once I asked, do you know quantum computing? He told, never dare to enter into quantum chemistry. It is very, very dangerous field. Meaning that it is very difficult to learn. That's what he told. And I respected my friend. I never entered into the quantum chemistry. But as an application point of view, I know that. Remember, sometime back I told computation without approximation. That is where we can directly apply into chemistry. The chemicals, the molecule states usually go into quantum states. The molecules, the number of quantum states of any molecule, that is exponentially huge. That will grow. Even add one molecule, that will grow. That will grow exponentially or explode. Those kind of things classical system cannot handle. So quantum computer naturally have that capability to represent multiple states in simultaneously. We call it as a massively parallel system because of the property called entanglement. Superposition, entanglement, these two quantum behaviors give the capability for massively parallel processing capability to quantum systems. So that capability is used by computational chemistry. Obviously, since it is chemistry, drug design, it is easy to make out that there also we are processing a lot of DNA, protein folding, those kind of things. Then cyber security, just now I told Peter Shor algorithm can break any classical security systems within 4 to 8 hours. Then financial modeling, if you are from feature and option, if you are doing feature and option trading, you know very well it is very difficult to build a portfolio on feature and option. See, normal share marketing is easy, somewhat you can manage with the classical system. But in goes to feature and option, there are various parameters to consider the volatility of the market. So those things can be done with the quantum computing. Then logistics optimization. The logistic optimization may look like very easy because we know very well this air or water or train or flight. These are the ways to transport goods from manufacturer to end user customers. But with the various parameters added to that one, this optimization problem will become a very complex problem which a classical system cannot solve it. That time, all these parameters will be put into quantum computing. That quantum computer will crunch the number in few hours and then give the output. The same problem will take days in the classical systems. Obviously, weather forecasting. These kind of complex problems can be done using quantum computing easily, effectively. That is the purpose of quantum computing. So now you understood. KG, I thought that one day quantum computers will replace classical systems. One fine day we will wake up and the world is no longer laptop, no longer desktop, no classical system, all are quantum systems. That never happened. That never happened. Quantum computers are powerful, but they need classical systems. Quantum computers are not going to replace classical systems. Indeed, for quantum computers to work effectively, we need classical systems. So quantum computing is giving only the processing power. But classical system has already established a lot of processing, data processing, display, what is called input output, data transmission, and number crunching. All those things already there in classical systems. Just to use those capability, only the processing task assigned to quantum computing. That is the industry focusing now. We technically call this as CPU plus QPU paradigm. So QPU alone cannot do anything. QPU means quantum processing unit, right? QPU alone cannot do anything. We need CPU. And also earlier, CPU and GPU, meaning that the machine learning problem, graphical problem, we have already GPU. So it will be CPU plus GPU plus QPU. That is the paradigm. As of now, the industry is planning to leverage the capabilities of various paradigms like classical systems, quantum systems. Both will work together and complement each other and get the work done. So so be clear that quantum computers will not replace classical systems. It is not possible. Quantum computers need classical systems to perform their operation. So be clear in this one. If someone says that quantum computers will replace classical systems, wrong. That is the wrong understanding. That never happened. Now, after hearing the applications, you may want to know what will be a feature of quantum computing. And see, some people when they're learning new things, they used to have that cavity. This is the new thing. Everything else is waste. This is the one thing. I won't tell like that. Quantum computers have their feature in their own domain, where see here you see quantum technology. It is not quantum computing. This is quantum technology. Quantum technology has quantum materials, quantum simulator, post quantum cryptography, quantum software, quantum cloud computing, quantum key distributions, quantum sensors, quantum networks, and quantum chips, quantum computing. These are all quantum technology. And when it's come to quantum computing, there are three generations. As of now, what we are having now, 2018 to 2028, non-universal quantum computers for low complexity simulations, because they are noisy. We are call it as a NISQ era systems. We call it the word with the NISQ era. NISQ. Noise intermittent systems, quantum systems. There is a noise always. Then second generation quantum computers are becoming much faster, more sophisticated. Yeah, few simulation methods. But 2031 onwards, we will have various quantum systems which can be used for commercial application also. This is what the industry is predicting about future of quantum computing. But here I would like to talk about each of this area. Quantum materials. This will help you to discover new materials. If you discover new materials, we can build energy efficient transportations. Like for example, a rocket, airplanes, they are consuming more energy just for the body to carry the body, not the passenger or not the object. That is 70%. Remaining 30% going for its own weight. But with the quantum materials, we can manufacture very lightweight, at the same time very strong materials. Then we can find out uh, construction materials, those things. Then quantum networks. Bristol is a city where they have built a quantum networks. The whole city is being built with the quantum networks now. And quantum key distributions, where remember I told you the quantum systems can break the security to protect our information from the quantum. There is a concept called quantum key distribution. There is a product in India, in Bangalore. There is an organization called QNU Labs. QNU Labs. We call it the QNU Labs. They are selling a product called Armos. That product will allow you to transfer the key using QKD, quantum technology, because they are using a photon-based product to secure, to communicate your key secured way. There is the product. Then quantum software, quantum cloud, post quantum. Post quantum, it is a classical system, but which can protect against, we are telling, but we are not sure. Then quantum annealer. These are all various quantum technology which will help. One thing is missing here. I know personally, it is called quantum sensing. Quantum sensing is a sensing method to sense the properties of elementary particles. Here I am by the word elementary particles, I am referring something called inside electron. There are elementary particles like quarks, lepton, muons, phonons, boson. These are all components inside electron or proton or neutron. That level I'm talking. So those elementary particle properties can be sensed. That is the quantum sensing. If you are able to sense that level, we can build powerful materials. So now you will realize we are talking something entirely different level. This is not our macroscopic level, we are entering into a quantum realm, which is inside an electron or proton. Always remember that quantum computing is subatomic scale. Now there is some commercial. In 2021, the global quantum computing market was 473 million. But in 2026, it will grow up to 1.76 billion. And in 2020, quantum computing startups were funded 1.4 billion. And over 80% of enterprises are looking to move forward with their quantum computing efforts with increased funding and resources. I have first-hand experience with this 80%. I know which organizations are spending their money on quantum computing efforts. I have the privilege to talk to industry leaders in the quantum computing. So I know very well how much organizations are betting on quantum computing. This is worldwide initiative. Now you can see global efforts 2023, 36 billion as of now. You can see here India is spending 80 8,000 crores, which is 1 billion. 1 billion US dollar India is spending. But whereas you see Singapore, they are spending 138 million. And Thailand, China, if you see 15 billion, they are spending 15 billion. India is spending 1 billion. Now you see the difference, right? And US is spending 3.75 billion. As of now, in the whole world, China is spending 50 billion. That they are the highest investor into the quantum technologies. Actually, for the curiosity, if you go and then search for worldwide efforts on quantum technology, this is 2023, right? You will see annual report 2022, 2021, 2019. You will see how much money pumped into the quantum technology in last 3 years. Last year it was $30 billion. I remember 2022 it was 30 billion. But 2023 just 3 months covered. Already we are seeing 6 billion increase. Now at the end of 2023, I don't know how much it is going to go. Maybe 50 billion. So these things convey one message. The industry is heavily spending money on quantum technologies. There are reasons because we are going to build powerful computing devices. That is one option, or that is one opportunity. Along with that, we have other areas. Remember, I showed you the quantum technology, quantum networks, quantum materials, quantum key distributions, quantum cryptography, quantum simulation. Those things are also getting funding because overall it's a quantum technology. That's why you can see here it is quantum technology, not just quantum computing. Now, after hearing all these things, now you may think, yeah, it looks very promising, very interesting. I want to pursue quantum computing as my career. See, the main reason why we are conducting this introduction session, some of you may be interested to pursue quantum computing. Some of you may not be able to pursue because it needs mathematics, all those things. But you can share this information to youngsters. Hey, if you focus, if you are good at complex number, linear algebra, and Hilbert space, you can pursue quantum computing. I personally conveyed this message to many of my friends, son and daughters, nephew, niece, and all. I motivated them to pursue quantum computing. But I am following this industry since 2004. So I know very well. Historically, I know a lot of things are happening. But I myself came to full-fledged career in the year 2022 only. It took more than 18 years for me to switch over to quantum computing career because the industry is not matured. But now this is the time. 2019 onwards, the quantum computing career is in the full, how to say, it is in full flow, full form. meaning that people started recruiting resources for various quantum skills. Earlier, it was predominantly PhD on mathematics and physics. These days, they started recruiting software engineers also. Software engineers with a good Python skill is high demand, but the production systems still using C++. That is the fact. I'm hiring 4 C++ developers, 2 Python developers. Now you can understand. That is the real industry. If you see my LinkedIn, you can see I posted hiring. That hiring is for C++ developer, not for Python developers. Because when we come for a high performance computing domain, we need C++ as the language. And I know I'm good at mathematics, linear algebra, complex numbers, Hilbert space, and I know programming language. I'm good at both C++ and Python. Is it enough? Of course, it is a good starting point, but we need a domain also. Whether you are from finance or cryptography or QML or hardware. As I told you, QML is my area. But for my company, I'm recruiting people with CAE. I will put it here, CAE, Computer Aided Engineering, and CFD, Computational Fluid Dynamics. These are the 2 areas as of now I am recruiting. Of course, Python full stack developer for the software team. That's what I told you. I have 2 requirements. That is for full stack developer, Python full stack developers with Python, Django, Django RESTful API, then React. This is a typical software skill set. In that skill set, I need 2 resources, but C++ developer, I have 4 resources. And we are also offering internship for C++ resources, but they must be passed out candidate, not students pursuing college studies. So these are the learning path. If now you will realize, my God, I think the quantum computing career is a costly affair. Costly means not by money, by efforts. Yeah, it needs a lot of efforts. And obviously you need a mentor. The main use of mentor is to stop. Because whenever you are doing self-learning, you will come across the one word. See, for example, if you go for linear algebra or quantum computing, you go to ChatGPT or you go to Google typing, okay, I can learn, or you go to Udemy, linear algebra for quantum computing. It will give a lot of points, but it is not necessary to read all those things. That is where you need mentor. Your mentor will tell, hey, you can stop here. You need not to go deeper into this particular topic. But in this particular topic, you go deeper, practice, solve the problems. So we need a mentor to stop us, because pursuing a quantum computing, you will have information overload. You will get avalanche of information. You don't know, oh my God, how much I have to read. So you need someone to help you to stop. Hey, don't worry, this is okay. You stop at this level. So that is what our strength. In MyQT, we know very well where to stop and what is the depth to delve into each topic. So our courses, guided instructor-led courses, will give you that opportunity to learn with the guidance. Okay, so the learning path really, when you look, it is promising, and believe me, as I told you, in 2025 onwards, the demand for quantum computing professionals will grow exponentially. The industry cannot meet that demand. The demand will be huge. If you start now itself, it will take some time. See, as I told you, because of the information overload and multidisciplinary or interdisciplinary skill level like physics, mathematics, computer programming, and of course your chosen domain, it will take minimum 9 months to 1 year to get a grip on quantum computing. So it is a lengthy process. You can't become a quantum computing programmer within 1 month or 2 months, within 3 months. yeah, I will join a course and then become quantum computing. It won't happen. Believe me, it won't happen. It will take minimum 9 months to 12 months. So you have to spend good amount of time on mathematics, good amount of time on physics. In parallel, you have to learn the programming, then understand the domain, apply this knowledge to build one POC or solution. Then you will become a quantum computing professional. Okay. Any questions so far? Can someone put the WhatsApp group? Yeah. Okay. Okay. Right. Yeah. Any question? Deepa, is there any question in the WhatsApp group? Okay.
Sir, good evening, Shivakumar.
Yes, sir. So, good evening, sir. Please tell me, sir.
Uh,
Thanks for joining, sir.
yeah, thank you. Actually, I thank all the few of my students also here. I think hope they are attending the session.
Thanks,
Mm,
sir.
so my clarification is that okay, still you are saying that Python is ruling majority, but of course you are searching for a C++ candidate.
Correct, sir.
So majority of the academic institutions has stopped teaching C++ in the regular curriculum.
Oh,
Most of the academic institutions is starting the programming even from Python last few years, and
okay.
recently again moving back to C and then Python, like that only it is going. But in between, people have skipped C++.
Oh, that is danger sign.
Hmm,
The
okay.
industry, the industry is still relying on C++ for building production systems.
Yes.
That is my first-hand experience. As of now, see, I know multiple languages because I started my career with the COBOL programming, COBOL, FoxPro, Clipper, Visual Basic, Visual C++, then moved on to Python, R language, Python and Julia. And now I'm learning a language called Rust. So this is my, of course, C++. These are all my skill set. Over a period of this 15 years of my career, I learned this much of languages. But still for production system, whenever it comes to production system, my first choice is C++ only. Because the performance, once you build a C++, link it, make it, deploy into server, the performance is something different. It will work very closely. Even Python, Java, they can't come near to C++. Of course, Julia is coming, but Julia is for scientific computing, but not for standard computing. That is the reason why I recommend, if you are very serious about computing career or any high performance computing career or quantum computing, I recommend learn C++. C++ is undisputable leader in the programming languages.
Okay. Okay. So
Yeah.
maybe I will teach my students C++. Maybe after a couple of years, they maybe become an expert.
Yes, sir. It is necessary,
Yeah.
sir. Whoever from academic, please do not ignore C++. And by the word C++, I am particularly referring to the OOPS concept.
Yeah, right, right. Since OOPS is
Yeah,
mainly introduced in C++ only.
yes. So
Yeah,
if you are learning C++, it should be OOPS. Without OOPS,
OOPS.
it is not necessary to learn C++. You can stay in
Yeah,
Python. So
yes, right.
now you will realize when you see the OOPS concept in C++, you will realize the power of programming language. You can simulate any real world situation using OOPS and C++.
Okay, okay.
Thanks.
So
Thanks
I
for the
have,
question, sir.
yeah. I have one candidate currently who is in the third year.
Okay, sir.
Skill set, he is saying that having knowledge on C++ only. So is
Uh-huh.
it possible to take him as a intern for a couple of 6 months to 1 year? And then based on his I strongly recommend that he will do extraordinarily well.
Sir, if
Okay,
it's
but
comes from
yeah,
your recommendation, I will
uh,
consider that person. But only thing,
well,
ask him to spend some time on OOPS or connect with me offline. I will give him the topics. What are the topics he has to learn in OOPS? Then I will assess his skills, then take into my internship pool, sir. Because students I will take only in internship pool. Once they complete the course, then only we will consider them for full time.
Yeah, right. The reason is that he is technically strong, but a little bit lagging in the communication.
That we can cover up, sir. No problem.
Yeah. But he's trying for 20 LPA only as of now, frankly speaking. He is number one in coding in the CAC cluster as of now. But due to the family background and schools and all, he is lagging in the communication only. So
sir.
So I told him that I will give some reference to enter into the tech industry, and again it's up to you to go ahead. Like that only
sir.
I asked.
With your recommendation, I will strongly support that student to excel in multiple ways, sir.
Yes.
That's great. You really appreciate your concern for your students. Thanks, sir.
Okay,
any other
thank you.
question? Any other question from any team members who are attending the session? Because we have left 30 minutes. If anyone needs a break, nature call, please take water, relax, come back. Because for the next 3 to 4 minutes, I will answer questions only. I'm not going to start the next topic.
Hey, hi, KG.
Hi.
Vikas this side. It's
Hey, Vikas.
good to see you after a long time. It's good to see you again.
Thanks, Vikas.
And I am seeing you are explaining really well as you were before. Same thing. I have a query which came into my mind. I'm not sure like how to put it, but yeah, I am seeing. See, 0 and 1, we are doing it from beginning, right?
Yeah.
And when to understand the superposition is something when it is 0 or 1, if I can say, right? But when we talk about classical computer and quantum computing, and quantum computing is only being built for this processing power, right? I want to know that this handshaking is going to happen, right? From classical computer to quantum computer, a handshake should happen, and then the data will come back. So I understand it from bits point of view. You talk about 0 1, but how this superposition is stored, I mean, like, whether this quantum computer is always in superposition state, or it comes down to not excited state as well, or it is always in that state. And how is there any interface present in industry which can actually if I will talk about processing, I will take some data, process it, and I will give it back. So that processing is to be done by QPU, but I will give something to CPU. There need to be an interface in between. So do how we have developed in this interface point of view, like that I need to know, right? Curious to know actually.
Yeah, good question, Vikas. It is insightful question. You are asking about the classical system and the quantum information, that encoding part, how it is happening and how it is encoded for enabling QPU to process. That is the question, correct? So
Right.
You take up this example. I want to come back to this Bloshbeer, where I explained is the 0 ket or 1 ket, 0 and 1. And our information, assume that we are having a position of a stock position or a feature and option in the portfolio optimization. The number is, it is currently being sold as 508. This is the number. So this number will be converted into binary number with some 0, 1, 0, 0, 1, something like this. It will be represented like, I'm not putting correctly, but some number. But when it comes to quantum computing, we will write it like this: kit 1010101101 kit. So this information, this classical information, will be multiplied by a matrix called 1 over root 2 1, 1, 1, minus 1. This matrix is called a Hadamard matrix. We will multiply our classical number with this matrix. When we multiply like this classical system will mathematically move to superposition. After that superposition is it's moved to superposition, the another qubit also will have the same position, or it will be 8 qubits put into next to next. Each one will be in the superposition. Then because of the superposition and entanglement, they have all the 0 to 512. All this position will be simultaneously exist in those 8 qubits. Am I making sense now? That is what the real quantum computer is working. When we are putting a number, a classical system encoded into quantum information, that will be a normal number like this only. But if you want to superposition, we have to multiply that number with 1 over root 2. This is called Hadamard gate. We technically call it as a Hadamard gate. With the H gate, if we multiply, that number will become a superposition. Then we will apply certain other operations, which are falls into quantum gates. Multi-qubit quantum gates or single qubit quantum gates will be applied on top of this data. Then that number will be processed massively parallel fashion because of this superposition. Then some result will come. That is when we will measure. So using the measurement operator, we will measure. So the measurement operator will give result. It will deduce the result from superposition to again a classical number. That is what happening in the real quantum computing processing scenario. Does it answer your question?
Yeah, it does. Great. Thanks.
Thank you.
KG.
Thank you. Thanks, Vikash. Any other question from any other members?
KG,
Yeah.
there's
Yes,
a
Deepa.
question in the WhatsApp.
Okay, let me check my let me check the WhatsApp.
Okay.
Say, as both Java and C+ is a swoops concept, but what makes C+ more recommended than Java? Yeah, because Java is using bytecode, right? We have JVM, Java Virtual Machine, in between your source code and then your the end processor by the microprocessor, right? The JVM is there because we know that Java uses bytecode approach. But in case of C++, when you link and make to the target system, there is no any intermediate code. It's directly compiled into the target microprocessor architecture, whether it is Intel processor or AMD processor or power processor or any other processor or ARM or embedded system, whatever it is. The C++ code will convert it into the target system in the compile and linking stage. But whereas in Java, always we are using a JVM. Of course, it is useful. JVM is giving better performance. But think about a performance of directing a rocket trajectory. You can't take chance, right? Few microseconds will impact. And think about building a medical system, medical diagnosis system, or medical scanning system. How that will support? Even a millisecond microseconds are very, very important there. Those kind of systems Java cannot support. That is why I recommend, it's not my recommendation, the whole industry is depending on C++. Does it answer your question? Hope the WhatsApp question I answered. Okay. Cool. Let us continue our next slide because we left with only 20 minutes. So after the software frameworks, applications are over, features over, and worldwide efforts also completed, and learning path also I explained. And here I explained what MyQT does. So your interest, you can interest us, and we are mentors having experience. The industry is very new. We need experienced people to guide you properly. That is where our strength. Here, if you want to learn Python, you can learn Python from here. There are few. We will share free quantum computing introduction courses also over a period of time. We are planning to release it on end of May for the general public. Now in the private preview. Once the preview is confirmed, we will release it to general public as a free course. You can enroll for that one. All those details will be communicated in the MyQT community WhatsApp group. You can enroll for the free courses. And when you are started building, so now we are entering into real programming concepts. So for quantum computing, you have to understand algorithms. Remember Peter Shor algorithm, which made the whole world turn towards quantum computing. Like this, there are many algorithms in quantum computing. This should be the first step you have to learn before entering into any quantum computing career. Without understanding the existing quantum computing algorithms, you cannot understand how the quantum computers is solving a solution. So these are the good starting points to understand how quantum computer is solving a problem or working mathematically. In this one, I am focusing on only one algorithm called Dice-Joshua algorithm, because Dice-Joshua algorithm one of the easiest algorithm to understand and the easy to build. Now we are going to a demonstration. So this is the hello. Anyone? Okay, right. So this is the Dice-Joshua algorithm what I built for one of the batch. I took a screenshot and then storing here, saving here. So this is how a quantum computing program will look like. This is called circuit approach, and this is the actual circuit. The problem is that the property of a given Boolean function, there will be a Boolean function, is that it is guaranteed to either be balanced or constant. A constant function return all zeros or ones for any input, while a balanced function returns zeros for exactly off and ones for other off. Our task is to determine whether a given function is balanced or constant. Here I will update with the zeros and ones. So the challenge or the problem of this Dice-Joshua algorithm is that you need to identify or determine whether a given function is balanced or constant. If you want to do this classically, you have to repeatedly run based on the number of bits. So that falls under O n square problem. That number of times you have to repeat. But when you do it in quantum computing, that will become O root n problem. So that is a computing complexity concept. Don't worry about that one. But as what I'm telling is, in summary, quantum computers will find out whether given Boolean function is a balance or constant very short. And this is the, if you want, see, if you don't like this kind of circuits, the actual program, Python program will look like this. Okay, now I'm going to demo this program, Dice-Joshua algorithm, on a IBM quantum computer. So it is one good thing with IBM quantum computers, you can get a free account in there. If you go to this login, you can create your own IBM account. Then from there, you can do the program. So this is my account. I'm going to do that. I have to stop my screen and then share again. Let me do it. I'm sharing again. I'm sharing my entire screen. Let me go to my Google Chrome. So I'm going to my IBM Q account. I'm one of the early adopters. This one is for demo purpose only. I have a production account also, but I never use production account for the demonstration like this. Now I'm logging into my account. We will finish in another 5 to 6 minutes. After that, I open for Q&A. So this is the composer. If I launch composer, it will, oh, this is different circuit. Let me remove these things. Click new. Yeah, this is my new circuit. I have 4 qubits. If I want, I can, sorry, I can increase my qubit also. Okay. So what is my Deutsch algorithm tells? I have to 4 qubits. I have to initialize first 3 qubits with superposition, and last qubit I have to X gate means not gate. Usually the qubits are 0 gate. When I get, say, let me put this is a Hadamard gate. I'm just drag and drag. Now you can see the positions are changing. So based on the superposition, it is changing. And here you can see this is 0 gate, right? This value is 0. If I put not gate, that X, see the circuit, what here you are seeing X, that is in the, here it is this symbol. This is not gate. So how I know that? If you click this I symbol, it will give you not gate. For every gate, you can click and then see this one. You can understand what is the gate, what operation is doing, all those things. So now you can see it is showing me what are the values. So now it is 1 because full 0, right? The value is 1. And this one is 50-50 because of the Hadamard gate. Now after that, what I have to do? I have to not for 0 and 2. So what I'm doing, I am applying not here and another not here. Then this gate, I am superposition H gate here. After that, I am inserting a barrier. So this is the barrier. This barrier will come only for 1 qubit. I have to select this and tick mark this one. So the barrier will be expanded to all 4 qubits. Now you can see in the Q sphere, it is showing all the possible values for all qubits. Now I have to 1 minute. Let me stop my video for a few seconds. Yeah. So now what I have to do? I have to do CX. This is controlled NOT gate CX for 0 to 4, 2 to 4, 1 to 4. So let me build this 0 to, see now I can't drag like this. So what I have to do? I have to click this bit, then target bit. I have to select Q3. Now it will become like this. And another CX gate. Again, this is also third qubit. Then another CX. Yeah, this is correct. After that, I am putting another barrier. So barrier are best way to, oh my God, barriers are best way to control your circuit flow. So predominantly earlier versions does not have this kind of capabilities, but now IBM made a good development here. After that, I have to build 2 NOT gates and then all H gates. So 2 NOT gates on qubit 0 and qubit 2. After that, I'm applying superposition for the top 3 qubits. I think that's it. After that, another barrier. Actually, I can copy paste also. What happened? Okay. So now after this, I am measuring. This is the measurement. So I'm measuring all the top 3 qubits. And at the end of the measurement, it will show you 0, 1, 1 is your final value. Now this is the circuit. after building the circuit, you have to run this on a real quantum computer. For that, or real quantum computer or simulator. For that, you have to go to the setup and run. Here you can select where you want to run the system. See, simulator or free. You can run any point of time. You can select the simulator and the number of shots, then click this one. Now it is running. After few seconds, you will get the result. See, now you see new job result came. If you go here, you can see this result. This is the completed task. It will show you the result. Now you may understand, but while seeing this, I don't understand anything. Indeed, you can't understand anything on the first attempt because it is a different kind of processing. We are used to see normal classical systems which will give a number as the input or number as the output, but here it is all signals. So, and then it's probability. Because of that one, we are seeing probabilities, or there is a state vector. In the state vector, we can see this like this, and this is a Q sphere. So it is now you will realize it is a different breed of problems. Input is also different, output is also different, even the internal underlying operations are also different, right? It is not and or not gate. It is something H gate, X gate, CX gate, CCX gate, swap, I, T, S, Z, T dagger, S dagger, P, RZ. They are not making any sense. Of course, when you are seeing this first time, it won't make sense. As I told you, you need to repeatedly read those things to understand these concepts. So now, if you want to run it on a real quantum computer, go here. If you scroll this place, you can see real quantum computers like IBM Bellum, IBM Lima, and IBM Beth, IBM Lagos. Like this, you can see a lot of quantum computers along with the number of qubit and then quantum volume. All those things you will see here. Then you select here. Then it is telling you, see, job limit 5 remaining. I have remaining 5 jobs. Then I can run on IBM Birth. It will take some time. You can see here. See, it is, you see here, it is queued. The queued job is still in queue. I don't know whether it will be completed before our session or not. Yeah, this is how you are running a real program on a real quantum computer. Okay. And with this, IBM account is created. Whatever I planned for today, 2 hours session is over. I have few backups, and then these are the web resources, and these are all not necessary. If you have any question, you can, when you explore this deck, you can understand. I will take few minutes. Say after the session, I will update the Dice Josh algorithm because the 0 and 1s are not coming correctly. I will correct them and then upload the PDF file into the WhatsApp group. There you can download the whole deck. Yeah. Now I open for Q&A. Anyone? I think someone is asking question.
Hi, Karthik ji.
Yeah. Please go
I
ahead.
just want to know, like, how when non-IT background person can make a career in this. I mean, how many like courses, what course we need to do and all. Could you please suggest me like?
Okay, if you are non-IT, are you from mathematics or physics?
I'm from I did from my inter I did MPC maths, physics, chemistry, but after that I just shifted to creative background like designing side. But right now I'm planning to make a career in this. Like I'm ready to invest my time and energy in this. So I'm ready to invest at least 3 to 4 years in this. I don't have any problem in investing my time on this learning.
Okay.
So I'm
yeah. That is the realistic goal, meaning that you told that 2 to 3 years, right? The reason why I'm telling, if you are not from physics, mathematics or software development background, it will be very difficult to enter into quantum computing career. You should be any one of these vertical, then only it is easy. So since you are not neither of these 3 things, I would recommend this flow. Let me type in the notepad. That will help you a lot. First thing you have to focus on programming, Python programming.
Okay.
Now you may wonder, KG, you told C++ by asking me to learn Python program. That is first easy to learn. So first enter into Python programming, learn Python programming. In parallel, learn mathematics and learn quantum physics or quantum mechanics. Then learn C++, or else you can ignore C++ also. Because the C++ I'm looking for the core physics people. For software engineers, they can stay within Python itself. Okay. After that, you have to understand quantum algorithms.
Okay.
Then one of the quantum framework. My recommendation is either Qiskit, or QSharp. So either one of these ones. So all these things, see, Python program is parallel activity. You have to do it. So if you start learning mathematics, that will take say 2 months, and quantum mechanics it will take 3 months because that includes necessary. C++ we ignore it. Quantum algorithms, that itself will take 3 to 4 months or 3 to 6 months based on your understanding. Let me put it 5 months for each. Then this framework, because this framework is coming from Python, right? I already learned Python. So this frameworks will take considerable time, maybe 5 to 6 months. So overall, if you add 10 plus 6, so 1.5 years it will take for you to switch over to quantum computing career.
Any institutions or like anywhere I can start right from basic level, right? What you're talking about is Python programming, learning mathematics and quantum mechanics.
There are many institutions. IIT Madras is starting a course coming June that covers all these things, but in 12 weeks period. 12 weeks plus another 12 weeks. And
it's an online program or offline, like we should be there?
Online. One day you have to go to Chennai.
Okay.
Weekly once you have to go to Chennai. That is the program they are following. That is really valuable. But considering your background, I'm little bit skeptical how much you can gain from that one. You talk to me later after the session. Connect with me in WhatsApp or connect to Deepa. Deepa will help you to identify because there are multiple organizations offering the course depending on your budget and then timeline and then your knowledge level. You have to identify the right mentor. I will help you as a mentor. I will help you to identify the right institute where you can pursue the course. Yeah.
Sure. Thank you so much.
My
Then I will
pleasure.
definitely.
Yeah, welcome. Thank you. Team, anyone having any question? It's an amazing audience you are. Thanks for joining on the World Quantum Day. And once again, wherever you are, whatever you are following, if you falls under New Year for you, Happy New Year to you all. And please keep in touch with us. You can contact either me or Deepa or Pradeep for your doubts. One of us will support you. We will try to identify the right course or right mentor to help you. And if any of you interested to be mentor, please join with us. We are connecting mentee-mentor relationship also, such that any capable person in this meeting, please join hand with us. Let us spread the quantum computing knowledge for the rightful candidate for their betterment in their career. Thanks, team. Thanks again. Have a great day. Bye-bye. Deepa, you can end the meeting.